Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to another lecture of this course on robust control. Over the past few lectures we've been looking at certain topological notions. We'll continue to do that in this lecture, but we shall wind up very soon, and then we shall move over to this very important concept of convexity, which shall be chasing us throughout this course. Right? So in the previous lecture, the last concept that we ended the lecture with was one of bounded sets, right? So we said that if you have a set within a vector space V, then we called it bounded if we could find a basis for B and subsequently an open ball corresponding to that basis, such that this set that you've been given, it could be contained within that ball. In other words, we could find a ball that is sufficiently large enough to contain a given set. In that case, the set would be called a bounded set. Okay. And finally, we ended that lecture by saying that if a set happens to be both bounded and closed, so closed is any set that is a complement of an open set. Of course, to reiterate, what is an open set? If around every point in an in a given set, you can cook up some neighborhood such that the neighborhood is completely contained within that set, then such a set is an open set and its complement is a closed set. So we are essentially looking for a set that is a complement of an open set and at the same time is bounded, and that is a set which we will term as a compact set. It is not generally the definition of compactness, okay, but however we'll let this pass, because it turns out that if the set we are talking about is indeed a subset of a Euclidean space, which is essentially what we shall be dealing with, in that case the idea of boundedness and closedness together imply compactness. Okay, it's not in general true, but in case of a Euclidean, in case a set is originating from a Euclidean subspace, Euclidean vector space, right, then we say that closedness and boundedness is equivalent to compactness, right. So that gives us this notion of compactness. But why indeed are we interested in this notion of compactness? And that is because of the following reason. Well, what is our reason for that? The reason being that, look, we were actually interested in this idea of being able to separate sets, right. So how does this idea of boundedness helps us? It turns out quite immensely. So what is this result that we are going to look at? Again, a result that we are not going to really prove, but we are going to just state and convince you that it's true. So suppose you have Q1 and Q2 are two subsets of this vector space V, right, and Q1 is bounded, okay, then Q1 and Q2 are so called strictly separable, if and only if, so it's a both way condition, it's a necessary and sufficient condition, the intersection of the closure of Q1 and of Q2 is empty, right. What does that mean? Just let us push our imagination a bit and try and understand, wrap our heads around this. So suppose if this one of these sets, say Q1, okay, I've chosen Q1 arbitrarily, it's because I'm biased towards the number 1 over the number 2 maybe, but anyway, So you could have just said any one of the sets is bounded. Now suppose that set is also closed. So in other words, if you have two sets out of which one is compact, right, then we can easily say that, well, the closure of a closed set is the set itself, right. So of course if it is compact, then it is closed, and if it is also bounded, because compactness brings with it the idea of boundedness. So if you have two sets, one of which is compact, then they are strictly separable if the intersection of the compact set with the closure of the other set is empty. If both your sets turn out to be compact, well, then it is very straightforward, right. So the idea why we bring in this compactness, this notion of compactness, is that if it is somehow given to us that a set is compact, then it is relatively easy to check whether that set is strictly separable with another set. Okay, that is where this idea of compactness, that is exactly the extent to which we shall be interested in the idea of this compactness throughout this course. Yeah, we are trying to separate sets, right. So that is exactly the reason why we are delving into this notion. Okay, there will be some practical utility which will follow soon, and precisely from this notion of utility, this utilitarian point of view, that we shall now turn our attention to the idea of something called convexity. Again, this is something that you are most likely familiar with. Maybe most of you have already heard of this defined technically. Even if you have not heard of this defined precisely in these many terms, you are certainly familiar with this, and you have certainly encountered convex sets at some point in time or the other. So what is convexity? Let us say, again, as has been the flavor throughout, it will be semi-formal. So suppose V1 and V2 are vectors in a vector space V, alright. Then we define the set L of V1 comma V2 as all those vectors V belonging to this vector space V which can be expressed as V is equal to mu times V1 plus 1 minus mu times V2 for mu in the closed interval 0 to 1. When I say closed interval, it means it includes its extremities, right. So 0 and 1 are also part of the possible values of mu, right. So that means V1 and V2 are also part of this set. Okay. So this is the set. Okay. So we have two vectors given by V1 and V2 in a vector space V, and given those two vectors, let us go ahead and define a set L of V1 and V2. Yeah. Why this L? Well, you might have easily guessed by now, this L denotes line, because this is after all nothing. If you think of it in the Euclidean space, it is basically a line, right. Line joining those 2 points is expressed. The segment of the line lying between 2 points is expressed as mu times V1 plus 1 minus mu times V2. Okay. Now, once we have this, suppose we have a set Q which is contained in the vector space, or which comes from the vector space V, such that for all, this sign means for all V1 and V2, for every pair of vectors that you can pick up from this set Q, yeah, we will have that it turns out that L of V1 V2 so defined as above, yeah, L of V1 V2 is contained within the set Q. Yeah. So then Q is a convex set. Okay. So, what is the idea essentially? The idea essentially is that if you pick out any two vectors in a particular set, yeah, and you take the line joining those two vectors in so to speak, right, which is given by the segment of the line, that is mu times v1 plus 1 minus mu times v2, yeah, and if the entire line, this set L v1 v2 is part or is contained within this set Q, yeah, and this is true for any arbitrary pair of v1 v2 that you might pick up in the set, right. So, you pick up any 2 points, any 2 vectors in a set, and if the line joining those 2 vectors is entirely contained within that set, then such a set is known as what we call a convex set. So, one of the obvious conclusions then is that any vector space itself is always convex, right. It is obviously true, because you take, it is because of the closure to addition and scalar multiplication, right. So, mu and 1 minus mu are just happen to be 2 special kinds of scalars, right. So, you take any 2 vectors in a vector space, scale one of the vectors by mu and the other vector by 1 minus mu. So, mu times v1 is part of the vector space, 1 minus mu times v2 is part of the vector space due to closure under scalar multiplication, and then mu times v1 plus 1 minus mu times v2 is also part of that vector space simply because of closure under vector addition, right. That is a property of the vector space. So, therefore, any vector space itself is always going to be convex. It's really a no brainer, right. But now, suppose we want to generalize this, yeah. So, suppose we want to generalize this. What do you mean by generalize this? How do we want to sort of generalize this? Okay. So, consider the following: summation mu I vi, right, I ranging from 1 through k, where summation mu I ranging from 1 through k is equal to unity, and mu I belongs to the closed interval 0 to 1 for every I, yeah, right. So, think of this, what is this then going to be? Think of a collection of points, so where of course and vi belongs to the vector space, needless to say, yeah, it's implied by it. What sort of an object have we got on our hands now, right? We are saying that this is a linear combination, certainly a linear combination of a bunch of vectors in the vector space, but it's a very special kind of a linear combination. For one, all these coefficients in this scalar multiplicants in this linear combination, they are all positive, constrained or rather non-negative, and also constrained to take values between 0 and 1. Additionally, what we are also imposing is that the sum of these coefficients is equal to unity, right. So, this is what we call a convex combination, not just a linear combination, it is a special case of a linear combination, it is what we call a convex combination, okay. But what is this object? So, suppose now we define, right. So now suppose we define this object, or rather we want to define this object. So, let us give it a name. So, we say CO of a bunch of vectors, let us say v1, v2 dot 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 till vn. Yeah, earlier we had taken k, I can take k, I can take n, I can take anything, let me take k to be consistent, okay. Suppose I define this set to be a collection of all those vectors v such that, okay, v belonging to the vector space v, of course, v belonging to the vector space v, such that such a v is expressed as summation I going from 1 through k mu I vi, with mu I belonging to the closed interval 0 to 1 and summation mu I is equal to 1 with I going from 1 through k. So, this precise object, yeah, now I am giving it a name, the collection of all such objects which are of the form summation mu I vi, yeah. So, as a very special kind of a linear combination which we are calling now convex combination. So, let me just put the term here in bracket, we call it a convex combination, okay. So, let us say we take a convex combination. So, all those fellows which are obtained as a convex, as a result of a convex combination of a bunch of vectors or points, we put them together in a set, and then this particular set we give it a name, yeah. I mean, it is all well defined so far up until here, right, that we are at least clear about. So, this we give a very special name, it is called a convex hull of set of vectors v1, v2 up until vk. So, I am given a bunch of points. If I want to cook up what is known as a convex hull of those points, then this is exactly a collection of all such points which can be expressed as a convex combination of these fellows, yeah. Sounds eerily similar, right, to the linear combination, yeah, and a bunch of all those, it's a subspace, right. So, you take members in the basis, for example, yeah, and you take the linear combination, and all the vectors that you can generate through the basis, they form the subspace spanned by that basis set, right. So, this is of course not a subspace as such in general, okay, but this is a very special kind of a combination, not just a linear combination, but a convex combination, okay. So, what are we going to call this, okay, and why is this important, right, why is this particular thing important. So, convex hull is not identical with the notion of subspace, although there are unmissable similarities if you've been paying attention to this. So, what makes this particularly interesting, you see, when we take the number of points, when k is equal to 2, when we take exactly 2 points, then this convex hull degenerates to this line that we have defined, this L of v1 v2. Therefore, this L of v1 v2 is indeed nothing but the convex hull of v1 and v2, right. In that sense, we call it a generalization. So, when I said that there is this generalization of this idea of this line, this is exactly what I meant, okay. So, you generalize this to k number of points and then you get the convex hull. So, why is this convex hull important? So, it turns out that if a set Q is convex, then it contains any convex hull of its points. Again, very loosely speaking, what I mean is, if a set is convex, you pick up any bunch of points from that set and you take its convex hull, yeah, then that convex hull will be entirely lying within the given set, okay. It will be contained by that set, okay. I mean, you can always try to convince yourself by drawing figures and trying to figure out if there is a convex hull of a given set of points in a set, right. What sort of a set looks convex, yeah. I am sure you have drawn shapes like these to convince yourself. Again, even if it may not be the best possible way to convince yourself analytically, at least the geometric picture would help, yeah. I would urge you to actually read up standard textbooks on convex analysis if you really want to get into much more details or rigorous depths of this particular topic. But for the purpose of this course, that is not absolutely essential. It is important to have the geometric picture in mind, for which this sort of an idea suffices, right. What we also say is that, well, now that we have this idea of a convex hull of a bunch of points, you see, every set need not be just a collection of discrete points, right. A set could be a continuum as well, right. It could be a continuum of points. So, next we go to this idea of, so far we have just seen a convex hull of a bunch of points, yeah. This is of course a special type of a set, but now convex hull of any set. So, the set need not be countable like here, the set need not be finite like here, yeah. So, it could be any set. So, now we extend this to the idea of convex hull of any set. How do we define that convex hull of any set? Okay. So, let us say, let us give that set the name Q, and then we say that convex hull of Q is defined as a collection of all those vectors which are contained in Q such that there exists, pay very careful attention. Okay. Now, we are not restricting this set to be countable or finite, right, but all we are saying is pick out all those points for which there exists n, and V1, V2 dot 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 till Vn. So, basically a finite collection of points. Okay, all we are saying is that you pick out a finite collection of points in that set, okay, where n is a finite number and V1 through Vn, these are indexed in this indices, right. So, the vectors V1 through Vn are indexed as 1, 2, 3 till n, yeah, such that V belongs to the convex hull of these points that you have now picked out. So, again, like we posed in the previous lecture also, here is the challenge. So, how are you going to collect together all these points constructively given a set, okay, and you want to check whether a particular point belongs to the convex hull of a set. What do? Take that point and figure out if you can pick out sufficient number of points within that set Q such that when you take a convex combination of those points in that set, can you satisfy the equation that V is given by summation mu I Vi, yeah, where mu i's are restricted to be between 0 and 1 in the closed interval, right, and summation mu I has to be equal to unity. So, if a point or if a vector V can be expressed as a convex combination of a finite number of vectors in a set, yeah, then that particular point belongs to the convex hull of that set. Remember, the convex hull of that set is generally a superset of the set itself. Obvious, no? Again, I will give you a geometric intuition, yeah. Only if the set is itself convex, then the convex hull equals the set itself, right. Otherwise, there is no chance that a set which is not convex and yet has its convex hull equal to itself, right. A convex hull will generally contain always more points than are there in the set, okay. So, remember this, okay, I think I need to modify this, yeah. So, I think, yeah, so this is this V. So, I need to really redefine this. This V is something that is coming from the vector space V, not the set Q, yeah, I should correct that. So, this convex hull of any set, yeah, this is not, so this V need not necessarily belong to the set Q, right. It can be anywhere, it can be even outside V. So, just to give you again a sort of a geometric picture, consider a set that looks like this, some sort of a curve like this, right, and then you take these 2 points here, say V1 and V2, all right, and take this point V here, which lies on the straight line joining V1 and V2, and therefore is in the convex hull of V1 and V2. So, remember this V, this is the set Q, this V belongs to the vector space V, but it does not belong to Q, but this V again belongs to the convex hull of Q, right. So, therefore, you can immediately see that this convex hull of Q not just contains every point in Q, it has to, of course, but it also contains points potentially that are not part of this set Q, right. So, therefore, the convex hull is a superset. Of course, the second observation is again pretty obvious, the convex hull of any set is a convex set. Again, we are not going to get into a rigorous proof of this, but why is this going to be true? Suppose it is not a convex set, it means that there exists some point which is basically a convex combination of points in the convex hull, yeah, but it is not part of the convex hull, but that precisely violates the definition of the convex hull, no. On the one hand, you are saying that this convex hull contains every point which is a convex combination of fellows in the set Q. But now I am saying that suppose there exists some point which does not belong to the convex hull, but can be written as a linear as a convex combination of points in the convex hull, right. So now think of it like this, suppose you have a set like this, yeah, and you choose its convex hull potentially to be the set, okay, let me use a different color. So now suppose you have, again pictorially I am doing this for want of a better illustrative method here. So suppose now this, you join this red thing here and then this modified set now becomes the convex hull. So this is the convex hull of Q, okay, whereas the original one was Q itself. So now if this is not a convex set, suppose, then what that means is that there exists, yeah, there exists some linear combination or sorry, a convex combination of points in the convex hull which is not part of this convex set, but then those points could either come from Q itself or could come from the convex hull. If they come from, if both those points you pick from Q itself, then by the very definition any convex combination of these points will be part of the convex hull. Suppose both those points come from the convex hull, not part of the Q itself, right. Then you see that this point definitely is a convex combination of fellows in Q. This point is also a convex combination of fellows in Q, right, yeah, and therefore any point in this line segment here, can you not also then write this as a convex combination of fellows here? Of course you can, right. So therefore any point here must also be part of the convex hull, right. So therefore the convex hull must be a convex set in itself, right. It's pretty obvious, no. You take any two points in the convex hull and if you have to just check whether the line segment joining those 2 points is a part of the convex set, right. So this is a point that belongs to say some summation alpha I vi, and this is say a point that say belongs to summation beta I, summation beta I wi, where the beta i's and wi's are points in the convex hull, right. Now any point that you want to express here, this is basically going to be mu times this is going to be 1 minus mu times this, and you add them subsequently. What does that give us? Yeah, what does that give us? You see the summation, the coefficients of these fellows here, this becomes mu alpha 1 plus mu alpha 2 plus dot 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 plus mu alpha some k1, and the summation of these fellows are 1 minus mu beta 1 plus dot 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 till 1 minus mu beta k2. But what do we know? What do we know about this? Right. So what can we say about this? This, then we take the mu common out from here. So we take mu common out from here and this sum is equal to mu. What about this sum? This sum is also 1 minus mu, right. So if we add both of these together we get mu plus 1 minus mu which is equal to unity, right. So therefore if we take a convex combination of the vi's k1 of these fellows and a convex combination of these wi's k2 of these fellows, then the convex combination of k1 plus k2 of those fellows, yeah, is basically a point here. So therefore this must be inside the convex hull, right. That is precisely the definition of it, right, because all these points are essentially coming from the set Q, right. So therefore we have kind of, actually I have almost proved it, you have to just write it down a little formally. I did not want to do a formal proof, so I have left it like this, but please convince yourself and try to follow this line of reasoning to convince yourself that the convex hull is itself always going to be a convex set. All that I have used is the definition of a convex set, nothing beyond that, right. So just put this, piece this together. I have deliberately not written this because it's at times good to do some exercises on your own, right, that way you will understand whether you are grasping these concepts. So take this as an exercise to write this down more formally, yeah. So take this as an exercise to prove that indeed you take any two arbitrary points in the convex hull and the line segment joining those 2 points will be always part of the set, yeah, part of the convex hull itself. So therefore, a convex hull, because of its very definition, is always going to be convex, right. The third and final point that I want to make here is that you take a convex hull of a set Q, it is going to be exactly the same as if you take the convex hull of the convex hull of Q, yeah. Maybe a little difficult to wrap your head around this the first time you hear this, but what is this saying after all? You already have a convex set, right. Once you have taken a convex hull of a set, you already have the convex set itself, right. So what this is basically telling you is, yeah, if you think about it a little, you take any arbitrary set, convex or not, and if you want to find out the smallest convex set that contains this set, then it is basically the convex hull. That is what this is saying. So read between the lines and try to figure out why this is true. I will give you a little bit of a hint on that line. So what this is basically saying is, the smallest convex set containing the set Q is the convex hull of Q, yeah. This is basically the implication. This is basically the important conclusion to draw from this, okay. So from the fact that if you take the convex hull of a set and then you take the convex hull of that convex hull, you will get back the same, it's basically the same as the convex set. In other words, you take a convex set and you take its convex hull, you will get the same convex set, right, yeah. So that is what this is essentially implying, okay. So with these things, we want to now put together a few more facts, which again I am not going to prove, but at the same time I am not going to just leave it like I am saying, therefore you have to believe me. Maybe if need be I will draw a picture or two to kind of convince you. So here is the thing, a set Q is convex if and only if, so it is a necessary and sufficient condition, if and only if the convex hull of Q is equal to Q. Okay, so for a convex set, of course, I mean you can just piece together this earlier discussion, right. So when you have a convex hull, it is a convex set, and therefore if it is a convex set, then its convex hull is indeed the set itself, right. That is precisely what this statement is saying. The next, and this is not along the same line of reasoning, but again this is, if you think about it, it is going to be pretty obvious. Intersections of convex sets are convex. Why should this be? Why should this be true indeed, right? So you take any vector that belongs to two convex sets, right? Yeah, and you take two such vectors that belong to two convex sets, right? Then must their linear combination also belong to both of those convex sets? Well, of course. See, you have V1 and V2 which belong to a set Q1, alright. So therefore, any convex combination, that straight line segment joining V1 and V2 must be contained in Q1. Similarly, you have V1 and V2 belonging to the set Q2, and therefore the straight line segment joining V1 and V2 must belong to Q2 as well. Yeah. But now if V1 and V2 belong to both Q1 and Q2, they are in the intersection of Q1 and Q2, and then the line segment is also in the intersection of Q1 and Q2, because the line segment must belong to both Q1 and Q2. So therefore every time you find two vectors that belong to the intersection of two convex sets, because those individual sets are convex, yeah, therefore the intersection must also be convex, right. Again you can draw some figures, some nice looking convex type of sets, yeah, on your piece of paper, and try and convince yourself of this, okay. So these are mostly the important points that I wanted to discuss about convex sets. Of course I have not done this as rigorously, I realize, as we had maybe covered some earlier topics such as those of linear algebra and maybe matrix theory, some properties and thereof, SVDs and things like that. but that is quite simply because whenever we shall be using these properties of convexity, it is these properties that shall involve, that shall really interest us more than essentially the techniques of proving these properties. So, we will invoke these properties later on when we want to prove certain results, but unlike the case of matrices or those results from linear algebra, where we will be using some of those manipulations, and therefore, it is important to understand the proofs or understand the constructive way in which to arrive at those results. But for this convex analysis part, I would put it that for this course, it is not particularly important for you to understand the proof completely, rather it is important to get a feel for or get a flavor for these sort of results that are true of convex sets, right. So, with that we can actually draw a line below this brief journey we have made into the domain of convex sets, right. Okay. Of course, this is not the end of all the convex analysis that we are going to talk about. Even in this lecture, we will see, we will take a short apparent digression, and then we will again come back to this idea of convex sets or something that is very relevant to convex sets, alright. So, here goes. So, now we go on to another apparently unrelated topic, but we will try to bridge this by the end of this lecture, and you will see the connection by that time. So, look, we have already seen what are linear maps or linear transformations, right, from a vector space, right. So, we have seen we take a point in a vector space, map it to some other point in another vector space, right. So, that is a linear transformation or a linear mapping from one vector space to another, and the mapping must satisfy the property of linearity. That is all that we want. Now, this linear functional is a very special class of such linear maps, where we say that we have a linear map from a vector space V to not just any vector space, but rather to the field, that is the field of reals, okay. And this is what we call as a linear functional. So, when your range or codomain is basically the field of reals or the set of real numbers, then we say it is a linear functional. A linear transformation or a linear map is then called a linear functional, and we will make a claim that this f is always onto unless it is the 0 map. Why is this true? So, I am saying that unless f is such a map which maps every point in the vector space to the origin, to the 0, origin means 0 in this case, right, 0 in the real numbers, this is always onto. In other words, for every real number I pick, real number, remember, is now the codomain. So, an onto map means that I pick any fellow in the codomain, and there exists a pre-image such that when I pass that pre-image through the mapping f, I will recover this element in the codomain, right. So, I am saying that unless this f is basically the trivial map which maps every point in the domain, the vector space, to the origin, to the 0, if it is a non-trivial map, then this is always onto. That means every point on the real line will have a pre-image. Why am I saying this? Because of the property of linearity I can make this claim, okay. How so? So, suppose there exists V belonging to the vector space V such that f of V is equal to some C not equal to 0. Remember that C is a real number, alright. Suppose it is a non-trivial. So, this part is just saying that it is a non-trivial mapping, alright. That is all this is saying. So, I have already said that this is unless it is the 0 map. So, we have already excluded the possibility that it is the 0 map by saying there is at least one vector which it does not map to 0, which it maps to some non-zero value on the real line. Then pick any arbitrary real number, say P, Okay. And then the claim is that there exists V1 such that f of V1 is equal to P. What allows me to do this? Remember, C is not 0. So, the proof of this claim is as follows. Take alpha is equal to P by C. Remember, C is not equal to 0, right? So, I can divide by C. So, take alpha is equal to P by C. Then let V1 is equal to alpha times V. What is V? V is basically that fellow which was mapped to a non-zero quantity C. All right. Hence, f of V1 is equal to f of alpha V. But because it is a linear map, I can pull out this alpha outside, and this is an operation, this is the scalar multiplication in the vector space V, but this is now a scalar multiplication over real numbers. That is what I can do precisely because of a linearity of this map. But then what is alpha? Let me substitute alpha. So, this is P by C times, and what is FV? By the given condition here, FV is equal to C. So, this is C, and C is non-zero, so I can cancel it out, right. So, this gives me P, right. So, therefore, I have found you this V1 such that when this V1 is mapped through this linear transformation or this linear functional f, I get back P. So, and this choice of P was arbitrary, right. I said I can choose any P, any arbitrary real number, say P, and I found you a particular vector in V such that it gets mapped to this fellow P, right. Okay, so therefore, we have guaranteed that this is going to be an onto map. Also, if you think about it a little and you apply this rank nullity condition here, so then dimension of V is equal to, what do we know about this? If this is the dimension of V, let us say it is a finite dimensional vector space, then we know that this is basically equal to the rank of F plus the dimension of the kernel of F. All right. So, what can we say about this? What is it exactly that we can arrive at, or what we can conclude from this? Look, this rank, again sorry, excuse me. So, this rank is nothing but the dimension of the image of F, image of F. But what is the image of F? Image of F is basically nothing but the real line, because it is an onto map. So, this is basically dimension of R, which is equal to 1. So, therefore, the dimension of the kernel of any linear functional, if it is a finite dimensional vector space, then the dimension of any linear functional is exactly going to be 1 less than the dimension of the ambient vector space. Okay. This is basically it, right. This is true of any linear functional. Of course, we are assuming that it is a non-trivial map, right. If it is a trivial map, then its kernel is basically the entire vector space. So, then the image of F is basically going to be just the origin, which is a 0-dimensional vector space. So, therefore, then this does not hold true. So, this is for, let me just clarify that, for F being a non-trivial linear functional. Okay. For F being a non-trivial linear functional, this is always going to be true. Okay. So, now let us push this a little forward. suppose f of v1 is equal to some real number, say, what should I pick? I am running out of variables to think of. Let us say alpha. This is of course a real number, right. So, suppose you take a particular linear functional such that it maps this particular vector v1 to this real number alpha, okay. And then this also implies that f of v1 plus v naught is equal to alpha for v naught belonging to the kernel of f. Remember, the kernel of f is a pretty big, so to say, for want of a better word, a pretty big subspace, no? It is precisely n minus 1 dimensional subspace when V is basically an n dimensional subspace, n dimensional vector space, correct. So, therefore, you can always choose many of these. I mean, it is abundant, the vector space V is abundant in a kernel, right. You are probably more likely to run into a vector that is basically in the kernel of f, yeah. So then what can we say about this? What is it basically then? Now, suppose we want to describe, so remember, the solution set of the equation f of v is equal to a, yeah. Then what sort of a set are we looking at? The solution set, that is, yeah, all right. What sort of a solution are we essentially looking at? Yeah. What we are basically then looking at is, you see, if we obtain any v1 which does not belong to, of course, the kernel, needless to say, we obtain any v1 such that f of v1 is equal to, rather have I chosen alpha, no? So, let me call this alpha, yeah, is not it? I have chosen alpha. If we obtain any v1 such that f of v1 is equal to alpha, then this solution set, let me call it S, is nothing but the kernel of f shifted by v1. Indeed, right. Why? Because see, we have already seen earlier that once you have one particular v1 that satisfies this condition f of v1 is equal to alpha, then if you keep adding members from the kernel of f to this particular vector v1, yeah, you will still keep getting more and more solutions that are legitimate solutions of this equation, right. So, therefore, if you want to characterize all such possible solutions, you cook up all possible members in the kernel, which potentially is probably an infinite set, right, yeah. So, then you just take this kernel, which is obviously a subspace. So, in the Euclidean space, you can think of this like a hyperplane, yeah, hyperspace, a vector space obviously containing the origin, and you shift it by v1. So, what I am saying in other words is, again let me draw a picture to fool you probably, okay. So, suppose this is in the 3-dimensional case. So, suppose you have this particular vector space, of course, which contains the origin, all right, it passes through the origin, yeah, and then we use a different color, probably black, yeah, and then you have this particular fellow v1 which says that push, shift this kernel. So then you get the shifted version of this kernel, yeah, exactly like this. Let me draw it with a dotted line. Yeah. So now this is my shifted kernel. So every point I pick on this kernel here, I add this vector v1 to it and I get its map here, maybe shifted version here. So this gets shifted to here, this point gets shifted to this point over here, like right like this. So if you can visualize what I am trying to draw here, right, then you see that this is basically the kernel of f, and this is the shifted kernel. Shifted by how much? If this is the origin, then this is what, where the origin has shifted to, it has shifted to v1, right. So therefore this shifted version of the kernel is what we call a hyperplane. Okay. Turns out these hyperplanes are objects of particular interest to us, right. So it's straightforward to see that just like this particular hyperplane or this kernel would have split up the entire vector space into two, the hyperplane, although not exactly a vector space, yeah, obviously it's not a vector space because it doesn't contain the origin, right. Any vector space must contain the 0, right. That's simply because you scale it up by the factor 0 and it must be contained, it must be closed on the scalar multiplication, right. So any vector space must contain the 0 of the vector space. So therefore the hyperplane is clearly not a vector space. Nonetheless, it still preserves the property of this n minus 1 dimensional vector space in the sense that the hyperplane splits up the space into two halves. I wonder where have we talked about separating halves in today's lecture, right? Well, just a while back, if you recall, we were talking about these separating, yeah, strict separation between sets. So it turns out that if we can cook up or if we can concoct certain hyperplanes, yeah, that separate two subspaces, then we are particularly happy. Not two subspaces, sorry, two subsets, right? Two subsets of a vector space. If they are separable by a hyperplane, then that's probably the best kind of separation there is. So we just a while back recall that we spoke about this idea of when two vectors or two subsets are strictly separable, right? We talked about this idea of one of them being potentially a compact set, right? And then we saw that this result told us, at least we didn't see the proof, the result told us that when you have two sets, right, and their closures are disjoint, then they are strictly separable, right, when one of them is bounded, right. So in other words, if you simplify that condition and you extend it for a little bit, impose some restriction, if one of them is compact, then by virtue of being compact it is clearly bounded, yeah, and then its closure is the set itself. So if one of them is compact, right, then you can always separate those two provided they are disjoint, okay, that is their intersection is empty. And then it turns out that now this hyperplane that we have now defined here will have a very important role to play in this so called separation. How so? So remember, how are we describing this hyperplane? Observe that by describing f and alpha, a hyperplane by defining or describing, whatever you call it, yeah, let us keep it at describing. Hyperplane is completely characterized. In other words, what I am saying is that if I have already told you what this linear functional f is, yeah, and what this number, this real number alpha is, I basically told you all you need to know about this hyperplane, right? Because then based on this you can actually find out what the kernel of this linear functional is, and once you know what the kernel of this linear functional is, right, then you can find out the solution that satisfies f of v is equal to alpha, and you shift the kernel by this particular vector v1, yeah, and that gives you the hyperplane, right. So, geometrically at least you will have the picture that what this hyperplane looks like, provided I tell you this pair f and alpha, right, they completely define the hyperplane which divides this vector space into two halves, right. So, suppose now we are going to kind of try to wrap up, yeah, this story that we have started about this separation earlier on in this lecture today when we talked about this compactness and these related notions, right. So, suppose we have two sets q1 and q2 in V, all right, and we say that let us say q1 is equal to the collection of all those vectors v in V such that f of v is greater than or equal to alpha, and q2 is equal to the collection of all those v in the vector space V such that f of v is less than or equal to alpha, yeah. So, then q1 and q2 are separated by the hyperplane described by the pair f alpha. Okay. Remember what is this hyperplane? F is not the hyperplane, neither is alpha the hyperplane. Okay. F is just a linear functional, alpha is basically what you are equating that linear functional to. Okay. So, together, taken together, this f and alpha, only then they define this hyperplane. So, do not make the mistake of thinking that f is the hyperplane, no, yeah, f is just the linear functional. So, do not get confused. Now, if you want strict separability, from separability, if we want strict separability, then we would say that instead of this A, we will replace this, replace A with A plus epsilon for some given epsilon greater than 0. In other words, if we are saying that there is some barrier, very loosely speaking again, yeah. So, if you say that, if you redefine that set by f of v is greater than or equal to alpha plus epsilon, yeah, then, so replace this, sorry, again why am I writing A here, this should be alpha, bad habit, yeah. So, if I am saying this f of v is greater than alpha plus epsilon, yeah, instead of just greater than or equal to alpha, while I retain q2 to be the same, right, then it turns out that they are now strictly separable. So, the other one is I retain as it is, okay. So, I change one of them, yeah, the greater than or equal to, I replace this with greater than or equal to alpha plus epsilon. Then it turns out that not just separability, but I also have strict separability through this hyperplane between these sets, okay. So, if you can get some such epsilon such that this is true, then indeed two sets are separable by a hyperplane which is described by this pair of linear functional and this particular numerical value of alpha, okay. But I must warn you at this juncture, such a separable or separating hyperplane, if it does exist, that is very well and good. Such a separating hyperplane may or may not exist. Okay. So, you may not always be so lucky. Remember, this is the caution. So, you might think, okay, hang on, we have this tool now at our disposal, let us get a linear functional, let us equate it to different values and see if the corresponding hyperplane that we get by the solution set, yeah, whether it actually separates these two sets, but you may be in for a rude shock. So, for instance, again let me draw a figure here. Suppose you have one of the sets like this and the other set like this, yeah, in the Euclidean space. Let us call this Q1 and let us call this Q2. Yeah, you will not be able to find a hyperplane that separates these two. Yeah. On the other hand, if you had separated them a little more, let us say this and this, let us say this is Q1 and this is Q2, then you could potentially have drawn a hyperplane through this, which basically strictly separates these two, right. So, what is the condition, as you might now have guessed from this, from what I am trying to hint at here, yeah, what is it that I am trying to hint at, what is it that I am trying to get at, yeah, from this particular picture. The point that I am trying to now motivate is that if, and this is the big result with which we will end this discussion today, when is such a separating hyperplane always possible to obtain? So, this is the big result, maybe I should mark it out, yeah, flashier terms, and that is why we have been interested in study of convexity, which will justify. We started with separability, we took a brief detour into convexity apparently, but then we come back and show that it is for this purpose of separating two sets that this convexity proves to be very useful. So, if Q1 and Q2 both are subsets of the vector space V, yeah, are non-empty convex sets, okay, such that they are disjoint, that is Q1 intersection Q2 is the empty set, yeah, then, so let me continue, this is a continuation of the sentence, comma, then there always exists some hyperplane that separates Q1 and Q2, yeah. Further, Q1 and Q2 are strictly separable if and only if, so this goes both ways, if and only if there exists a strictly separating hyperplane. So, that is a big message to take home. So, now we have an easy handle if those sets happen to be convex. That is why we have been so interested in convexity, because if you happen to have convex sets, then it is very easy to separate out two convex sets that are disjoint through a hyperplane. In the next lecture, we shall see some beautiful ways of characterizing these hyperplanes, right. We have already seen that they can be characterized by this solution set of a linear functional, or rather f of v is equal to alpha, yeah, by these pair f and alpha, right. So, we will next see how to cook up such typical examples of these linear functionals when your vector space V is either the n dimensional Euclidean vector space containing n tuples of numbers, or n cross n matrices, or even Hermitian matrices, okay. So, we shall next delve into that, and those will be particularly useful in our course going forward. Till then, take care, thank you.